Hi, and welcome to the 8th tutorial video for this term. This tutorial continues planar rigid body motion, but introduces acceleration analysis. The first problem states, the wheel rolls without slipping such that at the instant shown it has an angular velocity omega and an angular acceleration alpha. Determine the velocity and acceleration of point B on the rod at this instant. When analyzing a problem for both velocity and acceleration, you should start with velocity since it's not only easier, but it's necessary to fully resolve the accelerations. This is also the first time that we've had to deal with a rolling object. When an object is rolling without slipping, it's in a state known as pure rolling. One of the implications of pure rolling is that at the point of contact here, it has an instantaneous velocity of 0. I'll call this point R. Since we know the state of R from a velocity perspective, we'll use that as our starting point to solve the rest of the system. We can use our usual equation for relative velocity to find the velocity at point A. As I already mentioned, point R has no velocity because the object is in pure rolling. We're also told that the object rotates at a rate of omega in the positive k direction, so we can proceed to find the velocity of point A. Now for point B. We need to assume directions for the rotation of the rod and the velocity of point B. Since point B is constrained to slide along the ground, its velocity must be either to the left or to the right. I'm going to assume that it's rightwards, and that the rod rotates in the positive k direction. We can write out the relative motion equation and fill out all the terms, just like we learned in the previous video. Isolating the I and j directions let us find the rotation rate of the rod and the velocity of point B. Now we're done the velocity analysis part of this question, so we can move on to acceleration. Now if you think about a ball rolling on flat ground, it doesn't change height at all. The vertical velocity component must always be 0, so there isn't a vertical component to the acceleration of the center of the ball either. Therefore, we know that the acceleration of point O is purely horizontal. The acceleration of point O is related to the angular acceleration of the wheel by the radius, so we can solve for it easily. Now, for the first time, we can introduce the relative acceleration equation. This is the general equation we'll be using. You can replace A and O with any two points on the same planar rigid object. There are three terms on the right side. The first term is the acceleration of the reference point. The second term is the tangential acceleration of the target point about the reference point. Finally, the third term is the centripetal acceleration of the target point towards the reference point. If we expand the equation for points A and O, we can find the acceleration of point A. Now we can move on to point B. Again, we need to assume some directions, but this time it's for acceleration terms. I'm going to again assume positive directions for the angular acceleration and the acceleration of point B. If we work through the math, gathering terms in the I and j directions, we can find the angular acceleration and the acceleration of point B. Hopefully you can get a sense here that the math is not particularly hard. We're basically just using the same two equations, one for relative velocity and one for relative acceleration. What's important is to set up the equations correctly and to keep your directions straight. The next two questions will give us more practice with these equations. The second problem states, the center O of the gear and the gear rack P move with the velocities and accelerations shown. Determine the angular acceleration of the gear and the acceleration of point B located at the rim of the gear at the instant shown. Another way to think about this problem is an object that's in pure rolling, but the ground is moving as well. With that in mind, we can start with the velocity analysis. Instead of the bottom point of the object being stationary, like it normally would be for a purely rolling object, it has the same velocity as the rack of 2 meters per second leftwards. This is where we need to introduce the concept of an instantaneous center for a rotating planar object. Your textbooks and lectures probably give a more thorough explanation of this concept, but I'll do my best to summarize. If you consider the velocities of any number of points on a rigid planar body, they will all appear to be rotating around one single point, and that point might be outside the body itself. Now, how do you find the instantaneous center? Since we know that all the points appear to be rotating around the instantaneous center, then the instantaneous center must be located perpendicular to the velocity vector of each point. In the case of this gear, we know the velocity of 2 points, which is all that you need. I've also drawn the velocity vectors to scale, originating from each point. If we draw a line perpendicular to each velocity vector, we'll see that those two lines are collinear. If the two lines were not collinear, then the intersection of those two lines would be the instantaneous center. In this case, though, we can draw another line that joins the tips of the velocity vectors. This creates an intersection point that shows the location of the instantaneous center. The velocity of point O and point A both appear at this precise moment to be rotating about that instantaneous center. To find the position of the instantaneous center IC, we can use similar triangles and equate the ratio of side lengths for each triangle. Once the distance to the IC is known, we can find the rotation rate, which we can see is in the negative k direction. The velocities of the body are fully resolved now, so we can move on to acceleration. It's the same formula as before, but we have to be careful when we fill in the terms of the equation. We have to recognize that the acceleration at point A also has a vertical component of unknown magnitude. I'll assume that it points upwards. Working through the equation, we can find the angular acceleration. We can then use the angular acceleration to find the acceleration of point B. Lastly, we have problem 3. It states, the tied crank and gear mechanism gives rocking motion to crank AC, necessary for the operation of a printing press. If link DE has the angular motion shown, determine the respective angular velocities of gear F and crank AC at this instant, and the angular acceleration of crank AC. This problem is quite long, but it's really just a bunch of smaller questions put together. That is often the case for intimidating problems like this, and you can work through it step by step to keep things manageable. Since we have the most information about point E, that's where we'll start. And as I mentioned before, we always start with the velocity analysis. Solving for the velocity of point D is fairly straightforward using our usual equation. Point D is joined to point B through the main gear, which is called gear G. Therefore, we should next analyze the velocity of point B in relation to point D. I'm going to assume values for omega and VB. Point B can only move in two directions, thanks to the fact that it's rigidly connected to point A, which is itself fixed in place. The velocity of point B has to be perpendicular to the link AB. I'll just assume that it's in the positive I and j directions, and like usual, if I'm wrong, I'll simply find a negative magnitude after working through the math. So, we'll use the same old equation and expand all the terms. We find that point B actually has no velocity. This lets us answer the first part of the problem. Since both point A and point B are not moving, then the whole link ABC must not be moving. Next, we can use the gear relationship to find the rotation rate of the smaller gear, which is called gear F. This gives us the answer to the second part of the problem. Now that we have finished velocity analysis, we can move on to acceleration. We start by relating the acceleration of point D to point E. Here's where things get a little tricky. We want to find the acceleration of point B, but we aren't sure what direction the acceleration could be. We'll have to approach the acceleration of B from two different positions and equate the results. We'll start by looking at the acceleration of point B from point A. That requires us to assume an angular acceleration. Working through the math allows us to put the acceleration of point B in terms of the angular acceleration of link ABC. Next, we'll take a look at the acceleration of point B relative to point D. We can make all the necessary substitutions and collect terms in the I and j directions. Finally, we find the angular acceleration of link ABC. This question was pretty long, but I hope you can see that it is pretty simple to move through it step by step. So that's it for today's video. As always, you can contact me at this email address if you have any comments or questions. Thanks for watching, and I'll see you in the next video.